Goodman-Pollack-Wenger
Theorem.
Yeah.
Please.
Okay, thank you. Thank you for inviting me. I kind of invited myself. Okay, so when I was here last time, not that long ago, I spoke about geometric transversals because me and my co-authors were kind of getting back into this a little bit. And so this is a theorem about geometric transversals, and I'll explain this. And actually, so this is a theorem or this was a problem that I heard maybe in 2003 for the first time. At least a version of this, and then I couldn't solve it, and then somebody made some partial progress, and then some various things happen, and then so the G here is for Eli Goodman, one of the I would say founding fathers of discrete geometry, and he passed away last year, and there was a memorial conference for him, and actually Ricky Pollack also passed away the year before. So there was a joint memorial conference for those two who kind of founded the journal Discrete and Computational Geometry and were kind of founders of the field. And so I was asked to give a talk. And I wanted to talk about this theorem because that's one of the Goodman-Pollack-Wenger theorem is one of my favorite theorems of geometric transversals. And so while I was preparing that talk and the things I was going to present there, which was more like just about their work, I realized, oh, now I understand how to solve the colorful version. I was kind of very lucky, and so yeah, that's how it came about. But I had been thinking about it before, so it wasn't out of nothing. Yeah. Okay, so geometric transversals, it starts with from Hels Theorem. So let's say that's the starting point. Hels Theorem, and I'm just going to use some shorthand here to explain what Hels Theorem is. I can write it as follows. So this is a shorthand, so I'll explain what this means. And this is a theorem for, let's say, convex sets in the d-dimensional space. So it says that if I take a finite family of convex sets, this notation here means that any d plus one of them can be intersected by something zero-dimensional, a zero-dimensional point. Okay, so that's what this means. And that means that the whole family can be intersected by a zero-dimensional point. So that's what this notation here means, and it's an equivalence. Of course, if you can intersect all the members of a family of convex sets by a single point, any d plus one of them can also do that. And this is one of the most fundamental theorems of combinatorial convexity, and has lots and lots of applications, way beyond convex geometry also. And this is the starting point. And the reason I write a zero here is that in geometric transversal theory, we might want to change this to a higher dimensional flat. This is a zero-dimensional flat. Maybe I want instead to intersect by a one-dimensional flat, or a line, or a two-dimensional flat, or plane, etc. And this sort of line of investigation of generalizing Hels theorem, it dates back to a mathematician named Vincenzini, French mathematician, 1935. And actually, I'm not going to write down what he proved. He proved a statement about convex sets in the plane. He proved that T1 of 6 is equivalent to T1. Okay, so if every 6 of them have a one-dimensional line that intersects them, then all of them. And the reason I'm not writing that down is because that proof was wrong, and the statement was false. And so in general, for TK, so no Hels theorem for TK when k is greater than 0. So that was sort of corrected 5 years later by Santalo, who showed an example and said, look, this is wrong. Okay? But what he but he did show that something can be said. For example, if your convex sets are boxes like this, then there is a Heli theorem. Or if, and later, so then that started a whole industry. So, for example, Danzer proved that if the sets are unit disks and they're pairwise disjoint, then there is a Heli theorem. And so on and so on. So somehow if you start controlling the geometry of the sets, then you do get something. All kinds of geometric conditions have been considered. And a lot of positive results. But really, we would like to go back and understand what is going on if all we know is that the sets are convex, right? I don't want this extra condition that they should have this shape or be, these are circles or whatever, right? I don't want this, I just want statements for general convex sets. And that's the first such theorem, I would say the most general initial theorem. This is a name that's probably familiar to you. Hadwiger's transversal theorem. And so this is the same Hadwiger who has some famous graph theoretic problem named after him. I don't know if you know, but I mean he's not really a combinatorialist, or was not. He was a geometer, right, and worked in convex geometry and functional analysis and stuff like this. And so he discovered a theorem for any family. So he proved a theorem for disjoint, meaning pairwise disjoint, convex sets in R2. And what he proved was the following. So I'll write again with this connotation and explain what it means. That should be 1, 3. But I need to add something here, and this is what he added. And this means this is an ordering condition. I'm going to explain what this means. By the way, whenever I say convex sets, I mean finite collections of convex sets. Okay? And here, he requires them to be pairwise disjoint. And what is the ordering? So this means that you can take so if your family F can be given an ordering, so let's say C1 up to Cn. Okay? Now this condition says every 3 should have a line that intersects them, but that line should intersect them consistent with this linear order. Okay? So, in other words, for I less than j less than k, there should be a line that intersects Ci, Cj, Ck, but it should intersect them in that order. So Ci, Cj, Ck. Okay? So that's what this notation here will mean. That there is an ordering of the family of sets so that any 3 have a transversal, line transversal, which in addition intersects in that given order. If this is true for any 3, then there's a line that intersects all of them. Okay? So this is a very nice, not very difficult theorems, but it's very nice and it's relatively general conditions.
So will that line also be in the global order?
That's a very good question. And it turns out it doesn't have to be. That is, I'll give you the example. Excellent question. Now let me see if I can remember. Yes. This is going to be 4. And then now let me just do like this. Call this 1 and 2 and 3. Okay, so here there is, let's see, 1, 2, 3. 1, 2, 4. What am I missing? 1, 3, 4. Oops. Do I have 1, 3, 4? I don't. Let's make them come like this. Now it's very symmetric. Okay?
Yeah.
1, 2, 3. Now I can get 1, 3, and 4. Yes? Yeah.
That means that the formally trivial converse direction now is not so trivial. Is that?
So no, it is still another good comment. So the sets are pairwise disjoint, right? So suppose there's a line that intersects all of them. Of course, the line induces an ordering, and I just number them 1, 2, 3 up to n, right? So of course, if there is a line transversal, there is an ordering.
I see.
And if there is an ordering that is consistent on any 3, then there is a line transversal. But as Pascal asked, and we see now, believe, that doesn't mean that that line intersects in that order. Okay, so that's great. Then we understand Hadwiger's transversal theorem.
How do you get 1, 3, 4 there?
Well, these two are really close. This 1 and 3, they're really close here, right? Closer than I can actually draw. So there is a tangent here, here, here.
Oh.
Right? And same thing here. 1, 2, 4. 2, 3, 4. Yeah. But the whole point is any line that intersects them has to go get the number 4 in the middle and then intersect some other guy afterwards, right? So you'll never get 4 last. Is that clear? Okay, so actually, and Hardwickers' theorem, so this is a digression. Hardwickers' theorem is very, in a sense, he struck on something that was studied a lot later. So there's something called the geometric permutation. Let me put that up. So this is a side note. So geometric permutation, which is the distinct orders in which a line intersects n convex sets. So each such ordering comes in one direction and the other direction, and we identify those called the geometric permutation. And so people have studied the maximum number, so f n d. N sets, dimension d, how many different orders can you intersect such a family of n convex sets? What is the maximum number? And some known bounds are f n 2. The maximum is 2n minus 2. And in general, f n d 2 to the, no, n to the 2d minus 3 times the log n, n to the d minus 1, something like this. And that's some very, closing this gap in higher dimensions is an old problem that many people have tried to solve and very complicated. Okay, so that, but you see, that kind of motivated a little bit by Hadwiger's theorem about how many different orders could you actually intersect. Another note is, you might ask, well, what happens if you replace 2 by 3 here? You have the same ordering, and there are examples that show that no theorem will happen in higher dimension than 2 for lines like this. Okay? Okay, so then let me go over to the Goodman-Pollack-Wenger theorem. So G, P. So first I need to, so let me write in this shorthand again what that theorem says. So it turns out they discovered that, I told you this doesn't generalize to higher dimensions with line transversals. The way that it generalizes is with hyperplane transversals. So the correct higher dimensional version is the following: T d minus 1 ordered d plus 1 is equivalent t d minus 1. So this is for convex sets in RD.
Disjoint concept?
So yeah, so that originally Goodman and Pollack first proved this with a generalization of what disjoint means, which I'm not going to give. Then Wenger, he proved this theorem, removed the disjoint. And once he figured out how to do that, Pollack and Wenger removed whatever condition was added here. So now you don't need any. But we might need to say, what does ordering mean in higher dimension? That becomes the crucial thing here, right? And they had a way of describing that, something called order types. But I want to explain here a reformulation of what the condition is. Okay? So here the whole point is you look at three guys, I less than j less than k, in the linear ordering. So what does it mean that there's a line that intersects them? Well, another way of writing that is that Cj intersect the convex hull of Ci union Ck is not empty. Okay? So here, on your linear order, look at I and then j and k. It's precisely saying that I and k contain j in their convex hull. Or the j intersects the convex hull of I and j. And so then you just translate that over to here. Or, if you want to say contrapositive, suppose here, Ci and Cj does not intersect the convex hull of Ck, then the same thing happens over here. So if you can separate I and j from k, then the same thing should happen in the order here. I and j can be separated from k. So that is what this ordering now becomes. Okay, so what does it mean? So this ordering means the following, that there is a map. And what is a linear ordering? Well, if you have n sets, a linear ordering is just n points on a line. So instead, I should think of n points on some higher dimensional plane. Okay, so this ordering condition means a map phi from my family of convex sets into Rd minus 1, such that if I take a subfamily G in F, the size of G is D plus 1. Oh, sorry, I'm writing this wrong. So I take D plus 1 sets, and I split them into two families, right? And if the convex hull of the union of the G1 guys intersect the convex hull union of the G2 guys is empty, then the convex hull of the image G1 intersect the convex hull of the image of G2 is empty. Is it clear? No. No. Who said no? Ah. Okay, so let's go back to the linear ordering. So I look at my sets. Ci or C1, C2, C3. Okay? I can separate 1 and 2 from 3. So the convex hull of 1 and 2 is disjoint from the convex hull of 3. Then the same thing should happen in my linear order. So I and j should be separated from k. Right? Now, you could imagine the following. What if I have C1, C2, C3? I can separate any one from the other two. This is impossible if there is such an ordering, right? Because there is a j that cannot be separated from I and k, since I'm mapping this into the line. So now you should imagine, let's do 3 dimensions. Okay? So I have a bunch of sets in 3 dimensions, and I map each set to some point in 2 dimensions. Say like this. That's 1, 2, 3, and 4. Oops. Okay, so in my high dimensional space, suppose I look at sets 1, 2, and 3. So they're here, 1, 2, 3. This is in 3-dimensional space. I find a plane, has them above, and 4 is below. That's okay. 1, 2, 3 can be separated from 4. Right? But if this map is, so I'll call this a separating map, by the way. I'll call this a separating map. Now what if I separate, so among my sets, suppose I could separate 2 and 4 separated from 1 and 3. Well, that's not consistent over here. There's no way to separate 2 and 4 from 1 and 3 in this planar point set. Right? So this condition that there exists a separating map like this ensures me that there should be a plane, that the convex hull of 2 and 4 intersects the convex hull of 1 and 3, which means there will be a 2-dimensional plane that intersects them. And in fact, that I could choose points within these sets that matches locally this picture here. Is it okay? And of course, it gets a little more tricky to imagine this in higher dimensions, but if you know about what they call order types, this is consistent with called order types. And so the real realization, the original realization of Goodman and Pollack is that Hadwiger's theorem was just a 1-dimensional order type. The 1-dimensional order types are just linear orderings. And so then they realized, in higher dimension, you should just replace with a higher dimensional order type. And then you get such a nice hyperplane theorem. Okay. I think I might run out of time, but I see that now. So my goal will be to present the theorem. Maybe I'll have to skip the proof. Okay, so this is the introduction of geometric transversals. This Goodman-Pollack-Wenger theorem is from 1990, approximately. Okay. Hardwiger's theorem, 1957. Okay, so now let me switch. Those who know me a little know that I like something called colorful theorems. And the original one is the Hels theorem, colorful Hels. So this is kind of a combinatorial generalization of this original Hels theorem. It says the following. So now I have convex sets, convex or families, convex sets in Rd. And these will be denoted F1, F2, up to Fd plus 1. Okay? And the condition now is whenever I choose a set C1 inside here, and a set C2 inside here, and so on, a set CD plus 1 inside here, and I take their intersection, then this should be non-empty. Okay? This is called the colorful hypothesis. So instead of one family of convex sets, I have D plus 1 of them. Condition is whenever I take one guy from each family, intersection is non-empty. Then one of the Fi has non-empty intersection. So in other words, it's like Hels theorem, but I have now a number of families, D plus 1 of them. Usually they think of this as the red sets, the blue sets, the green sets. And the condition is whenever you take sets of different color, their intersection is non-empty. Conclusion is one of the colors, all the sets intersect, right? And this is a really nice theorem because the conclusion is about one of the Fi's. There's no hypothesis on any single of the Fi's, right? It's only about how they relate to each other. So the condition is transversal, but the conclusion is vertical. But you don't know which vertical one the conclusion happens in, right? And there are many other theorems. There's something called the colorful Cartedore, colorful Terberg, colorful Rodon, all kinds of things like this. And they have lots of applications, and many more applications than the original Hels Theorem or Cartedore theorem. And recently, that was since the 1990s, these have become much more important in some sense. We have discovered their importance.
Can you describe why they're important?
Yes.
Or it is
No. Okay. So, in the theory of intersection patterns of convex sets, we're given families of convex sets, and suppose many of them intersect, or there are certain intersection patterns that we are given, right? So the reason, okay, so here's the reason. If you look at Hels theorem, it's given a family, and all d+1 intersections are there, right? Now, if you think of that in terms of a hypergraph, this means you have a complete sub-hypergraph. If you record only which d+1 tuples intersect, if you want everybody of size d+1 to intersect, it means a complete hypergraph there. If you look at a situation like this is a multipartite hypergraph. I don't know anything about the intersections here. I only know about across. So if I were to encode this somehow as a hypergraph, I have a vertex representing each set in F1. So this is sort of V1 representing the sets here, V2, V3. And this condition says that this multipartite hypergraph is complete. And in extremal combinatorics, something called supersaturation says that if you have a very dense or a dense hypergraph, there will be many complete sub-hypergraphs like this, multipartite ones. But how many complete sub-hypergraphs will there be? Well, typically very few and very small. So these are sort of abundant everywhere in any dense hypergraph. The complete structures are not. That's why it's important. Okay, a good question. But I was hoping not to have to answer it. But anyway. And you do recover the original Hels theorem simply by taking copies of the same family. So that F1 equals F2 and so on. You just get the original theorem. Okay, so now comes the colorful. Okay, so what was missing? Well, oh, by the way, so this theorem here is quite famous. This is by Barane/Lovas. He sort of discovered should the conditions be, and he didn't know. His question was, find some formulation of a colorful version, right? And then so that was in 2003, and then in 2008 appeared a manuscript where somebody did in fact prove the colorful version of Hadwiger. And so let me state that. Colorful Hadwiger. Okay, so now I have a family of convex sets, and I'll write them F1 union F2 union F3. Okay, and now there will be an ordering on the union. Okay, and the condition, ordering, let's say like this. The condition is that whenever you take, so whenever you take sets of distinct color, so say you take a set that's green, you look at the ordering, then they should have a line that intersects them in this given order. Okay, so C, B, A. Okay?
So green means from F1?
It doesn't matter.
Oh.
You just take any, so this is, we call this a colorful triple. So take any 3 sets of distinct color. They will come in some order, right? And then you should intersect, the line should intersect them in that order.
So in particular, the ordering of F has nothing really to do. So it doesn't like say F1 is all smaller than F2
No,
and so
it doesn't say that, right?
Got it.
Or you could even put F1 equals F2, like copies of the same one. Yeah. Then you recover original Hadwiger, right? Right. So basically, you look at any tri-colored family, any 3 distinct colors, you look at their order, there should be a line that intersects them in that order. Right? Another way that you can say it is that this separation map. So phi separates colorful triples. Okay, so whenever you look at a colorful triple, so 3 distinct sets of 3 distinct colors, the map phi to R1 is a separating map locally on those 3. Then the conclusion is the standard one. One of the Fi has a line transversal. Is it clear? No.
Is this separating thing, is it a partial order?
Maybe you can think of it like that, since whatever order the red ones come in is they're sort of unrelated in some sense in this condition, right? Sorry, in this, when this is separating on the color traits. Does that answer your question?
I mean, I think I just wonder. I assume that.
Okay. Let's just think of it as a total order. Or in other words, you think of it like this: there is a map phi from F to R1, right? And whenever you take distinct sets of distinct colors, so a phi of A, B, C of distinct colors, so a triple which has all distinct colors, this map should satisfy the separations. Meaning, if the red and the blue can be separated from, green and red can be separated from the yellow, then the same thing should happen in the image over here. Is it clear? Actually, I don't like to think of it as orderings anymore. I just want to think of it as a map to R1.
So the difference here is, instead of carrying all triples, you just cared about F1, F2, F3 triples.
Yes, exactly. Yeah. But the ordering should be something global on the union of it. Yeah. Or a map like this. But the separation condition only kicks in when you're looking at triples of distinct colors. Yeah. Okay. I wanted to show you a quick application of this colorful version. So this notation means that I have a family of convex sets, any 3 have a line. Okay? And this implies, and here's some other notation, it means that, so I have n sets, every 3 have a line. There will be a line that intersects about 1/5 of the sets. Okay, so it's a fractional result. And here is the proof. Here lives my family of sets. Okay, it's a finite family, and I start with 2 vertical lines like this, and I start moving them in until I reach a position where the number of sets here, the number of sets here, and the number of sets here, roughly the same, differ by most 1. This is possible. I start here, there's 0 sets on this side, there's 0 sets on this side, all the sets are on this side. And I move in, the lines start intersecting some, start decreasing how many are in the middle, Then you stop when you're equalized. So can you believe that this is possible?
This is under the assumption that there's no line intersecting more than one.
Well, I haven't come to that yet. So far I only know that any three have a line transversal.
But if you try to squeeze,
Yeah.
if suddenly all of them are in the
Okay, that could happen, then I'm happy, right? Then I have a line that intersects a lot of them. So, okay, so now I will use exactly what you say. So suppose there's 20% that intersects this line, I'm done. Suppose there's 20% that intersects this line, then I'm done. So if not, there's at least 20% here, at least 20% here, and at least 20% here. Right? So let me color all the sets here red, all the sets here green, and all the sets here yellow. And then let me order these 1 up to 20%, and order these 20 up to 40%, and order these 40 up to 60%, or whatever numbers there were, right? Then I satisfy the colorful condition. Whenever I take a red and blue, there's a line that intersects them in that order. So one of the families has a line transversal. Right? So a simple application of this colorful Hadwiger.
So is there a full fractional version? Is there a full fractional version?
Yes,
Means
there is. So a fraction of these, yes, there is.
But do we know beta tends to 1?
It does not.
No. It does. You have an example that shows.
Yes. I mean, if beta tends to... So Hong is asking, suppose I have an alpha fraction of the triples have a line transversal, then, and that this beta, it depends only on alpha. And such a theorem does exist. But already when you tend to 1 here, you shouldn't tend to 1 here. There is no Hels theorem for line transversals. Right? But, okay, I can tell you when you have 1 here.
Oh, okay. What I mean is the ordered version. If you have.
That I don't know. That's a good question. That I would guess it is. I guess it does tend to 1. That I don't know. So a fractional ordered version, a fractional Hadwiger theorem instead of a fractional. Yeah, that's a good question. Okay, so let's see. Now I can state the colorful Goodman-Pollack theorem. And this time I'll try to be a bit precise. So, theorem, and this is, okay, I should say, the colorful Hadwiger was proven by Arocha, Bracho, and Montejano. And their proof doesn't generalize to the full Goodman-Pollack-Wenger one, but they conjectured that there should be a colorful version of this one as well. Right? And so that is the theorem I wanted to tell you. So here, F, this is a finite family, convex sets in RD. R goes from, so a function on the subsets to the natural numbers, and this is a matroid rank function.
So your natural number includes 0? Then
No. Maybe it does. If yes.
Yeah. Empty set.
Empty set goes to 0, you're right. Yeah. Then I have my separation map, which is a separation. This goes from F to R K. K is less than D. This is separation, separates on subfamilies let's say subfamily is G1 union G2, whose rank equals the size of G1 union G2. So in other words, on the independent sets of the matrix. I'll say in detail what, I'll go specifically into what this means. Then there exists a subfamily G, which has a hyperplane transversal and it's large in the following set that the rank of F minus G is at most K minus 1. K plus 1, sorry. So there's a lot of new concepts here, which is I'm not coloring anymore by colors like this. I'm actually, what this is called is a matroid coloring. Okay? And this type of matroid coloring was introduced by Kalai and Meshula. And you see, if I had, for example, families F1, F2, F3, right? I could form what's called a partition matroid, where the independent sets are, you take one guy from each color class, right? Those are the independent sets, right? And so I'm saying here that the function phi, so the ordering function, only sort of works, the separation condition only works on families that are, so this should be an independent set in the matroid. So I only care about, look at independent sets in the matroid, they separate consistently with this point set in RK. The conclusion is that this conclusion says that there is a subfamily that has a hyperplane transversal and it's large measured by the matroid. And how large is it? Well, let's plug it into here. So if I have 3 families, I have a partition matroid of rank 3, right? And I'm mapping this into K is 1, because I'm giving a linear ordering, right? And so K is 1, the rank is 3, but there's a family that has a line transversal such that if I remove that family, the rank of what's left over is at most 2, which means a whole color class has a line transversal. Maybe more, but at least one whole color class, right? So that's the colorful Goodman-Pollack-Wenger theorem in general matroid coloring.
Sorry, I'm confused with the statement. What's the, there you take K equal to B minus 1. Here, why you can take K equal to 1?
Actually the most general version of this puts an arbitrary K here. But it's really, so here I just have a map from each element of my, or each member of my family maps to a point in RD, minus 1. But I could fix a k-dimensional subflat inside here and just map everything there. Nothing prevents me from doing that, right? And so here I just include the k because I want the stronger, I need the k over here. Okay, but okay, if you want to read the theorem, you can just set k equals d minus. That's fine. Okay. And if you don't like, you guys like matroids, but if you don't like them, just think of partition matroids. That's just the original color full version. Right? And I think the reason that they introduce matroid colorings is that it's nicer. I don't know the real reason. I've never seen a real application of an arbitrary matroid here instead of color classes. So, like to your question, the real applications I've ever seen is this multipartite reason here, and it seems like the most useful matroid for this would be the partition matroid. But
so here when you say hyperplane transversal, the definition of that is just the rank function of this, or?
no. So there exists a family G G has a hyperplane transversal, and
Oh.
the rank, the G is large in the sense that when you remove it, the rank drops below k plus 1. Okay?
I see.
These are separate statements. There is a G that satisfies that it has a hyperplane transversal, and this
I see. So for partition matrix, G is like one color class.
is, yeah, it contains at least one whole color class. But see, the freedom here is, I could, for example, do 4 colors over there, right? But still, the rank, so k is still 1, but now I have 4 color classes. Then the statement says that there's a G that contains 2 full color classes, right? So I'm dropping down to the number which is related to this k here. So in the plane, I could maybe take more than 3 colors, right? 4 colors, 5 colors, etc. Okay. So I'm really running out of time.
Sorry, like in your original this colorful Hadwiger,
Yep.
there is an assumption that if it's like ordered by ABC,
Yes.
there is a line. Then where can I find that assumption? In your
That
table?
assumption is here. So this is the ordering assumption. So if I put k equals 1, it means precisely that I'm putting an order on the members of the family.
But then
And
if-
I'm saying that it separates on subfamilies that have full rank. And in this example here, what has full rank? Well, it's exactly one color here, or all distinct colors. If you have repeated colors, the rank drops.
so if I do pattern match, I can see what's written there.
So whenever I take subfamilies of distinct colors, that means that it's in an independent set, right? So one set of each color is an independent set. So that would be take 3 sets, and I look at those 3 sets, how do they map to R1? So let's say set 1 or set A, B, and C. This condition guarantees that they are distinct colors. This tells me that they have given a specific order because I mapped them to R1. And it tells me that B is in the convex hull of A and C, which means that in the geometric set, A is here, C is here. If I look at the convex hull, B should intersect, which means there is a line that intersects. Okay, so all of that, I mean, you're right. It's a lot to take in because I went a little quick. But all of that is hidden in the definition of this ordering function. Okay? And if k was 2, it means that you need to look at 4 sets that are independent in your matroid. Here is a partition. So A, B, C, D. So A and B cannot be separated from C and D. It means correspondingly that sets A and B and R3, their convex hull intersects the convex hull of C and D, which is equivalent to there being a plane that intersects them. So all that transversal information is hidden inside here. Okay. So then I had prepared how to prove it, but let's just say proof by Borsuk-Ulam theorem. And then maybe that's it.
That's it?
Well, isn't it supposed to end at 6:30?
5:30. 6:30 means 1 more hour.
5:30. Yeah, 5:30. Okay, so I can say 2 minutes about how you actually prove this. So first of all, you have your family of sets, they live in RD. And of course, the pictures, so first thing you do is you can assume all your sets, your convex sets are polytopes. This is technically easier to deal with. Okay? It's not a big restriction. And then you need to linearize the problem. So instead of living in RD, you move up to RD plus 1. Here's the origin. And here lives RD. And your original family of sets lives here. Okay? And then you extend your family to what I call a symmetric family, meaning each set reflected through the origin, so it also has a copy down here. Okay? So now, if your original family had n sets, your new family has 2 n sets. It also has a fixed point free involution. Every guy has a copy. It's mirror copy. What does a line, so in this picture, this is RD, so a hyperplane transversal here, this is dimension d minus 1. If you just look at that, that becomes a plane, that's a d-dimensional plane through the origin, right? And whatever you intersect here, you'll intersect the same copy down here, right? And then you can just extend your matroid function, your rank function, to this new family by parallel extension. I think it's called parallel extension. So this set here, union its mirror copy.
So you were defining matroid on like
So
twice many.
Exactly. Yeah.
Okay.
Just by parallel extension. And then the main thing here is you need to reinterpret this condition in the linear setting. So what does it mean? So let's go back here. So what does a separation mean here? So the condition is that if I have a set here, and a set here, and then this guy can be separated from these guys, and this is an independent set in the matroid, then the condition kicks in. Well, if you look at the mirror copy of these two guys, they will live down here. So this is a plane, or hyperplane. These two guys, if you reflect them to the origin, they come on here. So it means this guy and the two copies, they live on the same side. So the convex hull of these guys misses the origin. So the fact that they don't, you can separate these two from this guy, is equivalent to the convex hull of this guy and its mirrors are separated from the origin. And then my map phi, instead of going from RD to, or from the family in RD to RK, I need to go, this is an RK, this lives inside RK plus 1, and these guys got mapped to points here, and then the mirror image gets mapped to the mirror image down here. And so now the condition, separation condition, says that if you take an independent set of this matroid that can be separated from the origin, then the corresponding sets here can be separated from the origin. Okay. Okay, and then I need to start building. Then I build a simplicial complex here, and I map a. So I build a certain simplicial complex here, K. Okay, the vertex set of my simplicial complex is actually the sets themselves. Each set is a vertex. And a face of that simplicial complex is if you can be separated from the origin, the convex hull separates from the origin. So these three sets, they lie on one side of this hyperplane, and they form an independent set. That's a face of my simplicial complex. Then what does this ordering condition say? Well, it says that that simplicial complex maps into RK plus 1. And it actually maps into RK plus 1 minus the origin. Because whenever something was a face in my complex, it was separated from the origin here, which means it's separated from the origin here. So this map phi, I can, what's called an affine extension, I can build a map from RD plus 1 into RK plus 1. And it satisfies the natural involution, which is reflection to the origin. And then finally, this is the technical step, is I can also map SK plus 1 into this K complex by what's called a Z2, or a Z2 map. This is, I'm not going to explain it. Okay, but I can build this map. This guy maps already into here, and therefore I contradicted the Borsuk-Ulam theorem because I mapped from sk plus 1 to rk plus 1 without the origin. Right? Okay, so that I think I'll stop there.
Thank you. Questions? So is this the form that Arocha and others conjectured, or is this matrix form is?
No, so they conjectured only with the colors. So
Only with the colors.
yeah, only with colors.
And this
I'm not sure they were aware of the matrix colorings at the time.
I see.
And the matrix colorings, so the matrix colorings come up when I build this map, of course. I didn't use it there, right? When I build this map, I use the matrix colorings.
So if you just want to prove their conjecture without using matrix, then is it still working? Or
Yes, yes, it's the same proof, except that I realized, I actually first wrote the proof in colors. But then you always have to, then you're always repeating this word colorful, d plus 1 tuple, blah, 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 all the time. Monochromatic subfamilies and stuff like this. And it was much easier just to write with a rank function. And the proof is the same.
I see.
Because basically, a matroid, if you look at a matroid, so the main fact that you're using is that if you have a matroid M of rank, let's say R, rank R, right? And you look at the independent sets, that's called the matroid complex. The independent sets form a simplicial complex, and that simplicial complex is R minus 2 connected. So it's a topological connectivity of a matrix complex. This is sort of classical result, Bjorn-Lovas and Korte or something like this. Yeah. In fact, you can characterize matroids as, it should be a loop-free matroid, by the way. But you can characterize them in terms of this almost. The independent sets, a simplicial complex is a matrix complex if and only if every induced subcomplex is a wedge of spheres of this right dimension, something like this. So that's kind of what you're using. And when you have this connectedness, it means that you can build this map somehow. There are some technicalities along the way, but yeah. But that is crucial. But if I were to do it with colors, I still need to use the fact that the independence complex of, or sorry, the complex that you get from this colorful thing is this. So there is really no difference.
I see.
You're using the same fact that a matrix of a certain rank gives you a complex of a certain connectivity. It doesn't matter if it came from colors or came from an arbitrary matrix or what. That's all that I'm using. Yeah.
So the Borsuk-Ulam theorem that we use here is the one about general continuous functions, right? Continuous self-map.
Say again. The
Borsuk-Ulam theorem.
yeah.
Right. So I didn't quite get about the construction of the continuous function. Is it a really general continuous, or is it piecewise something?
Okay. So here. So what I have here is an abstract simplicial complex K, right? Each vertex is mapped to a point here. And I know that whenever I take a face here, so a face in this abstract simplicial complex, the corresponding vertices of that face, their convex hull is going to be disjoint from the origin. Which means I just take the affine extension. So this is just a map from the vertex set to a set of points. But I satisfy the condition that the convex hull of the image of a face is separated from the origin. So if I take the affine extension, that gives me a continuous map. And it will avoid the origin.
So it's kind of some separation properties. I see. Yes.
Yeah, so the separation is so that's why this condition here is crucial. That's how I can keep everything away from the origin to contradict the Borsuk-Ulam theorem. But you're right, basically this map this phi is just a combinatorial map, assigning each set to a point over there somehow.
That's exactly the point behind my question, because there are combinatorial versions of Borsuk-Ulam, right? Like Tucker, but you really. This is pretty
No, it's easier to just, because here you can just say take the affine extension and you're done, right?
I have another question. So 7 years ago when I came here, we met and we talked about realizability, right?
Okay.
And we talked about this Nikolai-Mnev result,
Yeah.
and that it is NP hard to decide whether some combinatorial property is geometrically
Right.
realizable. It's actually this complexity class existential theory of the reals.
Yes.
And one way of looking at it is that there's a gap between axiomatizing geometry and right. It's only necessary
Yeah.
conditions and not sufficient. Now my question is if we can throw in additional properties like second order properties like Hels Theorem or Hadwiger or colorful Hels Theorem or colorful Hadwiger. Does this get closer to a characterization of realizable geometries? It's a very
Okay.
vague question, but does it make sense?
It makes sense, but I don't know how to answer
Fair
it.
enough.
And
Yes.
maybe one reason, okay, this was something I wanted to add, it was in my notes, is actually this map does not have to go to RK.
Okay.
This map, so this is truly a combinatorial condition because I can also prove that it works as long when this map goes to any oriented matrix here. It doesn't have to be realizable. Okay, so, but I mean, I already ran out of time explaining this version. If I had to introduce oriented matrix, it would be take even longer, right? So this is really just a combinatorial condition. So that's why I think maybe at least this is not going to say anything about realizability because it doesn't really need this to be realizable at all. Just any oriented matrix will do. Any acyclic oriented matrix.
Any other questions?
Okay.
No, let's thank the speaker.